all the important things out of the way first. So the exams are graded, well, mostly. Are nearly done. So I'll have grades will be updated sometime this afternoon or early this evening. So keep that in mind. One other thing I want to point out, I noticed some of you haven't submitted all the assignments. So let me be clear. I will accept anything. So please, whatever you have, submit it whenever you can, and it will be considered. So let me remind you kindly to please submit any missing work. Don't forget that next week is really the last week of the term. So what we need you guys to do is we got to make sure we get all the work in, so we can to grade and all that fun stuff. So please do that at your earliest convenience. If you have questions about any of the problems, just ask. To be honest, I think we've done almost most of the homework problems we've actually done, I think, at some point. If we haven't done them, every single one of them, we've done nearly every type in class together. So please keep that in mind. And then the last thing I'll say, and a few of you reached out. So some of you were saying you didn't see your scores. So please double check your grades on Canvas. Make sure you have a grade submitted for everything. And if you're not sure why you got the grade you got, reach out to me and I'll let you know. It could be a typo. Maybe it's not a typo. Maybe you got the grade for whatever reason. So anyhow, please check into that. If you have any questions, let me know. I believe everybody's grades are updated, but I'm not positive. So it's going to be up to you to let me know if you can't see it. Okay, good. Good fun times. All right, so here we go. We need to do some math. And what I thought we would do is I was going to do the solutions to the exam, but I think what I'll do is I'll post that separately so that we can kind of pick up. Again, your time's valuable too. I don't want you guys to have to sit through me yapping. The learning comes from you guys doing work and then asking questions. So anyhow, we'll get the solutions on Canvas for you, either video format or PDF. Okay, so what we want to do now is, does anybody have a question before we get started? All right, so what topic are we on? We're getting to sort of the meat of the elementary uses of the derivative. Why do we as scientists or curious humans or mathematicians or engineers or whatever, why do we care about derivatives? Why do we need to learn how to compute them, and what are they good for? So that's sort of what we've been talking about. And so last class, what we did is we introduced extrema. So extrema is a word I don't know that I actually have used yet, but extrema is just sort of like a synonym or another word for maxes and mins. So that's what we introduced. So if I say determine the extrema of a function, that is one way of asking you, can you find the maximums and the minimums of a function? And let me reiterate why this would be important. There's lots of reasons why someone would care to do this. But let's use the time-old example of making money. If I own a business, my goal is to maximize revenue and minimize cost. And so from that standpoint, that is how you can interpret why this is important, or think about why it's important. Okay, so we were able to answer some questions about this. So we stated and discussed some important theorems. I'm not going to go through them again. You guys can check out last class. And what are these theorems used for? Well, these theorems are used to determine extrema, or help, I guess is a better way, any extreme. So perhaps the one that we should at least state right now is what we called Fermat's theorem. And so here's the key idea. So the candidates for, remember, we had local and global extrema. So basically what we told you is Fermat's theorem says if you're a max or a min, so if a max occurs for some function f, it's say some point c, that means that when you plug c into the function, the number it spits out is larger than all its surrounding neighbors. And what we learned is the derivative must be 0 here. And the reason for that is quite, you know, you can do it analytically. You can write down the definition of the derivative and show it's 0 by that argument. But often it's just better to draw a picture. If I draw what a local max is, here's a local max, and let's imagine that this is, now we draw a tangent line here. So, and even if I, you know, I can, just for even completeness, I'll put my x and y axis here. So if I come over here and I say, you know, here we have a max at x equals c, a local max. And notice that the slope of the function at c, since it's a horizontal line, is 0. So that's sort of what Fermat's theorem is saying. What are these critical numbers? These are the points where the derivative is equal to 0. Does anybody have a question about this? So the very important word here to keep in mind is the candidates. We're not saying every critical number corresponds to a max or a min. What we're saying is if you're going to be a max or a min, you must be a critical number. So if you really think about the logic of that statement, it's a one-way street. It doesn't work both ways. So what we have to realize is that there is a process to determining max and min. So let's write down this question that we sort of ended with last class. So given, you know, f of x, how do we determine any local extrema? Now, we solved this problem if we restricted our domain. If we restricted ourselves to a closed interval, A, B, closed, then this problem is not difficult to solve. We did some examples, and then we asked you to do some for homework. However, if we don't restrict ourselves to a specific domain, the problem is a little more difficult. And so we have to think about how we would solve that. And it really comes down to using some deductive reasoning, just like we did before. And this deductive reasoning can really, without all the fancy symbols, can really be understood by looking at this picture. You know, if I go back to this picture and say, again, if it's not clear, just imagine that I have some, you know, this blue curve is representing some function. We'll call it y equals f of x. And if you think about all the tangent lines near C, like what if we have a tangent line, you know, what's the tangent line look like over here? It looks like this. And then what's a tangent line look like over here? It looks like that. And then over here, what's the tangent line look like? Well, say you picked a point over here. If you look at those tangent lines, think about the sign of them. This guy over here has a positive slope. This guy has a negative slope, positive slope. And when we think about the sign, we alluded to this last class. We alluded to the shape of a graph seems to be completely determined by the sign of the derivative. So let's keep that in mind. So we mentioned in this last time that the shape of the graph is determined by the sign of the derivative. And in fact, more is really true. So what we're really going to find out is the properties in graph of f are given by the sign of not just f prime, but also the second derivative. So the first and second derivative are sort of like the information holders. They hold all the information about the function f. So why is this true? Well, we can state formally, or not necessarily formally, but in a logical way, we can tell you why. So let's recall the mean value theorem. From last class. And what we want to do is apply it to a specific scenario. So let's think about a scenario and let's see what the theory, what this mean value theorem can tell us. What information can we get from it? So let's assume that f prime of x is greater than 0 for all x in some interval I. All right. So let's pick 2 points. So I'll call them x sub 1 and x sub 2. So I'm going to pick 2 points in this interval. So the mean value theorem says there is a number c satisfying. So let's say c is going to be between x sub 1 and x sub 2. So remember, the mean value theorem, it facilitates, not facilitates, it's a bad way, it tells us that this c exists. And we drew a picture last class to show you the intuition behind it. And if you draw pictures, then you'll say, okay, this seems a reasonable thing to conclude. So I take 2 points in an interval. I am assuming that the derivative's positive in this interval. And so I'm going to apply the mean value theorem. So C has to satisfy this, but more importantly, what it does is we have this very nice inequality. We know that f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1 has to be equal to f prime of C. Now, what do we know about f prime of C? Well, we don't know what its value is, but we do know what its sign is because we've made an assumption. We have assumed that it's positive. So then by that assumption, we can make a conclusion about something here. So since f prime of C is greater than 0, we now know that f evaluated at x sub 2 minus f evaluated at x sub 1 divided by this guy is greater than 0. Okay, so what does that mean? Well, if you think about it, it might just look like a bunch of scary symbols to you, but it's actually holding a very, very important piece of information. And so if we assume x sub 2 is greater than x sub 1, then the only conclusion we can make is that f evaluated at x sub 2 has to be greater than f evaluated at x sub 1. That is just elementary arithmetic. If the whole fraction has to be positive, then the numerator and the denominator both have to have the same sign. But what does this mean? Well, this tells us, well, I guess let's write it a different way. So let's just conclude this for now. Okay, so let's draw a picture now of what we found. And maybe our intuition can take over. So if we draw what we just did, we have some x sub 1, and then we have x sub 2 over here. And what we've concluded is that when I plug x sub 1 into the function, the output has to be less than when I plug in x sub 2. Now, I didn't assume anything about x sub 1 and x sub 2 other than they're in some interval I, and that x sub 1 was less than x sub 2. So the only conclusion I can make is that the graph must go like this. There's no other options. If you try to draw that blue curve any differently, then you're not drawing what we just verified on the previous page. You're drawing something else. Now, instead of thinking math for a second, think, intuition, think English language, think reading left to right. If you were describing that blue curve to someone, as you go left to right, the English words that come to your mind might be it's going up, or more, formally we would say increasing. So this suggests a definition. So a couple things we get from this. So the previous work and pick suggest a few things. The first is a definition, and the second is a useful theorem. So they might not suggest to you right now, but once we write these down, hopefully you'll go back and say to yourself, oh, okay, yeah, I get what this numbskull's saying. Okay, so let's go to the next page. So suppose f is defined on an interval I. If x sub 1 is less than x sub 2, and f evaluated at x sub 1 is less than f evaluated at x sub 2, for any x sub 1 and x sub 2 in I, we say f is increasing on I. So, it's going up, it's increasing, you're making money. The temperature is increasing, whatever interpretation you want. If your function is describing some physical thing, or it can be describing anything, in this sense, we say it's increasing, it's going up. And then if x sub 1 is less than x sub 2 and the opposite holds, that is f of x sub 2 is less than f of x sub 1, we say f is decreasing on I. Okay, so this is good news, because what we just did previously is sort of a sketch of a logical proof of the next theorem we're going to state, which is going to be a very important tool for us when we're trying to determine extrema. So theorem: if f prime of x is greater than 0 for each x in I, well, what that argument we used with the mean value theorem logically shows is that if the derivative is positive, then the function itself is increasing. And then if f prime is less than 0, if it's negative, then f is decreasing. So the derivative, as we've alluded to now a few times, the derivative tells us when we're going up or when we're going down. So it's often useful to just apply this to some things you already know. For a simple example, this is what I would encourage you to sort of do. So I don't know what this means, but I've often said it. So keep these examples in your back pocket. They'll help you remember these things. So let's start with f of x equals x. Notice f prime of x is equal to 1, and that is always greater than 0. And so if you look at the graph, the graph of this creature, as you know, is a line of slope 1. So what's interesting is this guy is always increasing. For example, you guys are, this is a line of slope 1. It goes through the point 1, 1. It goes through the point 2, 2, etc. So if you have a question, please stop me. Now let's look at the next simplest, I would say, of functions. After a line, let's take a parabola. What's the derivative here? Well, the derivative here is 2x. Now note, 2x can be positive or it could be negative. It's going to depend on what x is. So if x is greater than 0, then f prime of x is greater than 0. And if x is less than 0, f prime of x is less than 0. And so if we look at the graph, it will be in agreement with this, because all this is a parabola. For example, it goes through the point 1, 1. Is not the scale, but 2, 4. And if you look over here to the left of 0, you would say that the curve's coming down. So you're decreasing. And over here, you're going back up. So you're increasing. Does anybody have a question about these two examples? So these are baby examples that I would I think help you to understand these concepts. So, and they're not hard to just throw in your back pocket, not physically, but sort of, the proverbial back pocket. Let's do one more of these examples that I would encourage you to have in your back pocket. What if f of x is now x cubed? Well, what's the derivative here? Here the derivative is 3x squared, which is either greater than or equal to 0. So what this tells us is the following. So if x is not equal to 0, then f prime of x is greater than 0. Thus, f is increasing on negative infinity to 0. And then we remember this symbol, this union symbol. So it's increasing everywhere but at 0. And if you draw the graph, you'll say, oh yeah, that's right. That's what the cube function's graph looks like. So what does this function, what's the graph look like? Well, you might not remember it, but if you do, it looks like this, comes up, sort of tries to flatten out, and then goes back up. Does anybody have a question about this? Just to remind ourselves, it goes, for example, through the point 1, 1. Goes through the point 2, 8, etc. All right. Any questions, comments? Anybody want to scream and yell? We only have 4 classes left. So sad. So sad. There's someone's chiming in. You're not backtracking. What's up, Heather? And so or ask your question, your pregunta, as they say. Okay, give me a second to pull it up because I don't know what that is. You said homework 8-1C, right? Give me 2 seconds. Okay, what about it? There's absolutely infinitely many. So that's a trickier problem because most of us are weak. We'll do that. We'll do that example before we finish today. Actually, yeah, we can look at that. Let's do some simpler ones first, and then we'll get to that. But you're right. There are infinitely many critical numbers, and the reason is the sine and cosine oscillate forever and ever. So it's sort of what happens is when you're not so how do I say this? When you're not familiar with properties of sine and cosine, it makes it hard to do this problem, but we'll show you how to do it in a second. Okay, so good deal. Okay, so let's do an example that's sort of in between the ones we just did and what you're talking about for the homework one. So all right. Bear with me 1 second. So switch pages. All right, so here's an example that's sort of so here's what turns out. So the type of problem that is, or the type of skill you want to have is something along the following lines. So we want to determine the intervals of increasing and decreasing for a function. So let's say for f of x, and let's do this one. How about negative x to the fourth over 4 plus x cubed minus x squared. So let me clean that up. Looks trashy. So what does it mean to determine the intervals of increasing and decreasing? Well, it means precisely what we're asking. When is it going up? When is it going down? Can you determine these intervals? And this is really, it's not a difficult thing to do. It just comes down to some algebra, typically. We'll show you how to do it, and then we'll get to the problem that you were referring to, Heather, because that one's a little more involved because it requires your knowledge of things in calculus. Okay, so how do we go about doing this? So first, we need to get the critical numbers. Why would we want to do that first? Well, the critical numbers are where the derivative is equal to 0. And so what that tells us is those are the points where the derivative changes sign. What are the options for a number? A number can be 0, or it can be positive, or it can be negative. It can't be both. It can't be all three. It can either be one of the three options. So what we're going to do is, if we want to find when you're going up, increasing, or going down, decreasing, that means we want to find when the derivative is positive and when the derivative is negative. And so a good way to logically get at that is to start finding where the derivative is 0. So that means I want to solve f prime of x equals 0. And this is what I asked you to do on homework 8, problem 1, find the critical numbers. So what's the derivative here? Well, it turns out that it's negative x cubed plus 3x squared minus 2x. And we want to know when that's equal to 0. And so now what started as a calculus problem now turns into an algebra problem. We have to solve this quadratic, or excuse me, this cubic. And so the first thing that I'm going to do, because it makes my brain a little easier, is I'm going to pull negative x out, and then I'll be left with x squared minus 3x plus 2. So now your algebra is probably not as strong as mine. No one expects it to be, but hopefully you can see what I did there. And if you're not sure what I did, distribute that minus x back through. If you take negative x and multiply back through, you'll get what you started with. And we can go one step further if we remember our algebra, because this quadratic actually factors. How does it factor? Well, it factors in the x minus 2 and x minus 1. You can verify that for yourself. So from this little bit of algebra, what we've concluded, and I'll put it over here so we don't have to switch pages, we have 3 critical numbers. X equals 0, 1, and 2 are critical numbers. Does anybody have a question about this? Okay, so we didn't finish the problem yet. All we found are the critical numbers. Okay, so the only thing that remains though is to make what we call a sign chart. Now this is something you would have done in an algebra class. You might have forgotten it. That's okay. I'll show you how I do it. Does anybody have a question? All right, so I'm going to remind you what f prime is. This is going to make it easy for us. It's negative x times x minus 2 times x minus 1. That is a factored version of the derivative that we factored. And why that's useful is because it easily allows us to make a sign chart. So here's how I would make a sign chart. I take a number line, and what I'm going to do is I am going to put my critical numbers on this number line. So what are my critical numbers? I have 0, 1, and 2. And so what I'm going to do is I'm going to divide my number line into separate intervals. Because here's what I know. I know that the derivative at 0, the derivative at 1, and the derivative at 2 all spit out 0. So what I want to know is what happens at these test points. So I'm going to choose test points. I'm going to choose -1. I'm going to choose positive a half. I'm going to choose 3/2, and then I'm going to choose the number 3. So if you're not sure why I chose those numbers, or you're not sure what I'm doing, please ask. Okay, so here's what I know. I know that if I plug -1 into the derivative, what do I get? Well, if I come up here to the right, if I plug -1 in, I get 1 times -3 times -2, so that's 6. And I don't really care what the value is, but what I do know is that's clearly greater than 0. And then if I plug 1/2 into my derivative, well, this one might be a little trickier to do in your head. All right, so when you plug 1/2 in, what do you get? Well, I get -1/2, and then it's going to be times negative something times negative something. So I have negative times a negative times a negative, and I don't care what it is, but what I do know is it's less than 0. I don't care about the value, I just care that it's less than 0. And by the same token, if I plug 3/2 into my derivative, I'm going to get a positive number, because I get negative times positive, which is positive. And then last but not least, when I plug 3 in there, I don't care what I get. You plug 3 in, you get -3 times 1 times 2, so you get -6, but it doesn't matter. What matters is that it's negative. So what we can conclude from this chart is the following. we're increasing on, let's be very, very clear here. F is increasing, not F prime. F is increasing on negative infinity to 0, union 3/2 to 2, or excuse me, not 3/2 to 2, excuse me, from 1 to 2. And decreasing on 0 to 1, union 2 to infinity. I get all that information just from this chart, this sine chart. Okay, does anybody have a question about this? So some other things that should be pointed out from this work that we just did on that example. So we can actually deduce more about F from the sine chart. First and foremost, what we can deduce is F has a local max at 0, 0 and 2, 0. F has a local min at 1, what happens when you plug 1 in there? You get 1 minus 1, so you get negative 1/4. And what else we can do, which is quite fascinating, is we could sketch the graph. I mean, just using that chart that we did, we can literally get this information. So you might not see it as clearly as perhaps someone at the level of experience that I have, but whoa. But just looking at that chart, here's what we can deduce. We can deduce the graph looks like this. We know these points it has to go through. We know it has to go through 0, 0. We know it goes through 2, 0. And we know it has a minimum at 1, negative 1/4. So just using that chart and some deductive reasoning, what we deduce is that the graph looks like this. It comes up, goes down, comes up, and then goes back down again. There's no other possibilities for that graph based on our analysis. So think about that, and if you have a question, let me know. Going once, going twice. Third time's a charm. All right, so let's before we get to another example, let's state a very important sort of consequence of the previous example. So the previous example illustrates the logic behind the proof of our next theorem. So what is this theorem? Well, we usually give it a name. We call it the first derivative test. For extreme. Let's state it. So assume f prime of c equals 0. So let's assume we have a critical number. If f prime changes sign, if it changes from positive to negative at x equals c, then x equals c is a local max for f. And then, of course, if f prime changes from negative to positive, at x equals c, then x equals c is a local min for f. Now remember, c is not the value of the max or min, it's where the max or min occurs. So it's very important you understand the context of this. But if you go back to the picture, it's really easy to remember these ideas. Basically, we're saying is if you go from increasing to decreasing, you have a max, a local one. And if you go from decreasing to increasing, you have a local min. Clearly, if f doesn't change sign, then there's no max or min. So now we have solved the problem of max or mins. We know how to do it now. The first thing we do is we find critical numbers, and then we ask ourselves, does the derivative change sign? If it does, then we have a max or a min, depending on how it changes sign. If the derivative doesn't change sign at that critical number, then there is no max or min. Ooh. Does anybody have a question about this? Okay. So, whew, what else can we say? Well, Okay, so looking at pictures, and when I mean pictures, I mean graphs. And investigating suggests we can learn more. So what do I mean by that? So let's draw a picture. Let's draw a typical local minimum. So let's just draw some picture here, and let's sketch what a local min might look like. So here's a local min. So this is C comma f of C. What the heck? Interesting penmanship by so local min at x equals C here. So let's be very clear. This graph right here, this is some graph of some function f of x, y equals f of x. So let's look at some tangent lines. So we know the tangent line at the bottom is has slope 0. But in the tangent line over here, for example, is positive slope. Tangent lines over here are negative sloped. And so another way of saying that is the following, and this might take some thought on your end. So note, f prime is increasing. So notice what's increasing. I didn't say f is increasing, because f is not. F is decreasing and then increasing. But look at f prime. F prime is the slopes. So as I read left to right, my slopes are negative, 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 but they become closer to 0. Then they flatten out, and then they go positive, positive, positive. So f prime is increasing. So what does that mean? This means f double prime of x has to be positive. So I hope that you really take some time to think about this. F goes from decreasing to increasing. However, f prime is increasing on the interval that I've drawn this picture. So what this picture tells us is that the second derivative might hold information about maxes and mins too. So this picture suggests a few things. It suggests that the second derivative is affecting things. And it also suggests that perhaps we make another definition so that our minds can sort of take English words that we're familiar with and connect them to this visual. So that's what we want to do. So here we go. This is super duper wild, but it is what it is. So the previous page suggests a definition and a theorem. Let's do the definition first. If f prime is increasing on some interval I, we say f is concave up on I. So there's your new word of the phrase. F is concave up. And look at the picture. It's opened up. So how we describe that is we say it's concave up. That's the mathematical term for this sort of valley. Okay. And then if F prime is decreasing on I, we say F is concave down. All right, now we can state the theorem, which is very analogous to the first derivatives in increasing and decreasing. So if F double prime is greater than 0, I guess we got to be more specific. We have to be assuming it's on some interval. So the second derivative being positive on I, then F is concave up on I. And then, of course, if F double prime is negative on I, then F is concave down on I. Wowzers. Does anybody have a question about this? And we're going to do an example in a second. Okay, so let's go back to the example we did before, since we already so let's go back to f of x equals -1/4 x to the 4th plus x cubed. We already found the critical numbers, minus x squared. And so the derivative, as we found, was -x cubed plus 3x squared minus 2x. And we, as you remember, we factored this as -x and then x minus 1 and then x minus 2. What's the second derivative here? The second derivative is -3x squared plus 6x minus 2. Well, when does this thing equal 0? This thing equals 0 when, of course, x equals, you have to use the quadratic formula here. So it'd be -6 plus or minus the square root of 36 minus 4 times -3 times -2 all over 2 times -3. Which, you know, you could work through that if you wanted, but it you know, it's just as easy to solve it using a calculator, which is what I'll do right now. What I should do is I should just do it on a calculator, but pretend I did it in my head. And you guys would be like, what is that? So if you solve this, if you work this out, you get 1 minus 1 over root 3 and 1 plus 1 over root 3. Those are your two solutions. And by the way, you know, you can approximate these. This one is approximately 0.423, and this one is approximately 1.57. So why am I finding where the second derivative is 0? Well, these are the points so these are the places where f double prime can change sign. So it's not necessarily that it'll change sign, but it can. And I guess I should be more careful. You know, the places that it changes sign is precisely these numbers right here. So what I could do is I can mimic what we did in the previous problem, and I can make a sign chart. Only this time I make a sign chart for the second derivative. So if I put my number line out there and I have my two ugly looking guys, but you know, this is 1 minus 1 over root 3. And then over here I have 1 plus 1 over root 3. And then I make my sign chart. So I need to pick some numbers, some test numbers. Well, let's use our brain and let's pick some easy ones. Let's say, okay, what number do we know is between them? Well, the one that's between them is clearly 1, so that's good. And then let's pick something over here. How about 0? That's always easy to plug in. And then something over here, let's just pick 2. So what is the second derivative evaluated at 0? Well, if I go to the previous page, the second derivative evaluated at 0 is -2, which is clearly less than 0. So if I plug 0 into the second derivative, I get -2, which is negative. Here, if I plug 1 in, I get 3 minus 2, which is 1, so that's positive. And then if I plug 2 into the second derivative, I'm going to get a negative output. So what I can conclude from this is that f is concave up on this scary looking interval, and concave down on -infinity to this number union 1 plus 1 over root 3 to infinity. So those numbers are, they're ugly aesthetically to the eyes, but they're numbers nonetheless. And you should use the exact values with these radicals. You shouldn't use the decimal approximation. You should use the exact values. Does anybody have a question about this? Here's another interesting thing to take from this, because that is also going to be of use. So this example tells us more. So let's summarize that. So what does it tell us? Well, it tells us we can test for local extrema using F double prime. So we can state that as a theorem, which we will. And this one is called the second derivative test. For extrema. So let's assume we have F prime of C equals 0. And this is a technicality, but we need F double prime to be continuous. So there's a couple options. One option we can have, if F double prime evaluated at C is greater than 0, then F has a local min at X equals C. The second option is if F double prime of C is less than 0, then F has a local max at X equals C. And then lastly, the third scenario is if F double prime of C equals 0, the test is inconclusive. It means you can't use it. You have to try another test, the first derivative test. Whew. So we actually, there's a lot more that's happening here than just me stating these things we call theorems. There's a lot of really cool things happening here. What we're essentially telling you is just by being able to compute the first and the second derivative, you can describe all the geometric properties of the graph of a function. And even more, you can analyze a function and determine its behavior solely through working with the first and second derivative. So it's hard for you to appreciate that as a student who's just learning it because you've just been bombarded with all this information. But in fact, it is true. So it's worth us stating that. In summary, we can completely analyze a function f and accurately draw its graph just by studying the sine of the derivative and the second derivative. Now, if you've ever studied physics, I guess this wouldn't surprise you from that sort of interpretation, because basically what we're saying is an object that's moving, everything about it is completely determined by its acceleration and its velocity, the first and second derivatives. But nonetheless, even from an abstract mathematical perspective, this is quite fascinating. Everything that we would want to know about the function f can be determined from us studying f prime and f double prime. And so we're going to give you some problems for homework to work on that kind of stuff. And hopefully you'll ask questions. You know, it's interesting. Nowadays, we have super good software and technology that can do a lot of this for us. You know, but 15, 20 years ago, you know, we didn't have any of that. You know, 20 years ago, you had to spend a lot of money for a calculator to graph. Obviously, the most efficient way to graph a function, most functions at least, would be use Desmos because it's free and it's easy. But what we're telling you is you can now do it by hand. You can graph any function as accurately as you could want just by studying its derivatives. So, you know, that's one way of sort of not one way, but if you're looking for, you know, who cares about all this, well, there you go. There's one thing that you can do. Now, of course, you know, it's not the only thing we care about. We're going to show you more applications soon enough, but you have. Before we go back to some examples, does anybody have a question or comment? All right, so maybe, I'm sorry, not Becca. Heather, you were the one that asked about this problem from the homework. So let's look at it. We'll answer the questions that the homework asked, but we'll see if we can go a little further. So I believe it was what? Sine times cosine? Yeah. Okay, so we have this function. Beautiful little creature, sine x times the cosine x. And so in the homework, we asked you to find the critical numbers. So the derivative requires the product rule. So this becomes, the derivative of sine is cosine. So you get cosine x times cosine x, and then it's minus sine x times sine x. So if you wanted, you could clean this up a little bit. This is cosine squared x minus sine squared x. And we would like to know when this is equal to 0. So when is it equal to 0? Well, the only way this is equal to 0 is when, one way to think about this is when the cosine squared equals the sine squared. You just take one guy to the other side. And then you can divide both sides. Suppose I divide both sides by 1, I get 1 is, excuse me, by cosine squared, I would get 1 is equal to the tangent squared. So this is the equation I want to sort of study right now. So a lot of times, if I give this problem, students might get to this point and then you sort of fall apart. And that's okay, because most of us don't really have the experience with the trigonometric functions that we should have. So when is the tangent 1 is what we're essentially asking. Well, from elementary trig, you might remember this happens at pi over 4. So x equals pi over 4 is a solution. Now, most students in Calc 1 don't know that off the top of your head, but you should know that. And if you don't, or you're saying, how did you get that? Well, one thing you could do is plug it into a calculator and verify it, or you can look at a unit circle, or you can get in your time machine, go back to trig class and say, I remember this. No, I'm just kidding. The problem with making your time machine is you have to be good at math and physics, right? And that's kind of like circular reasoning because we're struggling at math right now. So x equals pi over 4 is a solution. That's one solution, though. Turns out there's infinitely many solutions. So since tangent is periodic, there are actually infinitely many. So you might have some trouble with this, but if you're struggling with it, just go to like Desmos and graph the tangent function. And you'll see, hopefully you'll get what we mean by by periodic. And so what are the solutions? Well, x equals pi over 4 is a solution. But if I add 2 pi to that, the period, what is 2 pi? Well, that is well, I guess technically, let's be a little more specific. What is the period of the tangent? Well, the period of the tangent is pi. So the next solution would be pi more. So if I add pi to that, I get 5 pi over 4. If I add pi to that, what's the next one? Well, if you want to get the next one, then that becomes 9 pi over 4. And you'll notice that there's a pattern now. What's the next one? The next one is going to be 13 pi over 4. And that pattern goes forever and ever. But there's also the negative values. So if pi over 4 is 1, if I now subtract pi, you also get negative 3 pi over 4. And then if I take pi away from that, what's the next one? Well, if you do it in your head, that becomes negative 7 pi over 4. And then what's the next one? You can start to see the pattern now. This is negative 11 pi over 4. And then that pattern continues forever. And so, Heather, that is why when you look at the graph, you see there are infinitely many critical numbers, because there are. By the way, there's a real cute way, and this is really usually something difficult for students to sort of grasp at this level, but the pattern is x equals pi over 4, and then what we typically do is we'll write this, 2k minus 1, where k equals 0 plus or minus 1 plus or minus 2 plus or minus 3, etc. So anytime k is an integer, whether it's positive or negative, you plug it in there and you're going to get that, when k is 1, you get pi over 4. What happens when k is 0? You get what? And then don't forget, we also, well, I guess I should have been a little more clear, because you're not just getting the tangent to be 1, you also need to know when the tangent is -1. And so that happens at, so if you go back to the graph and investigate that, you'll see that's -pi/4 and 3pi/4. So this is a challenging problem, especially if you're not strong in your trigonometry, your trigonometric stuff. So let me make this clear, because I don't think you I guess I can clean it up here. Really, you're not just wanting to know when tangent is 1, but you need to know when it's also -1, because -1 squared is 1. So when does tangent equal ±1? I don't know if that makes sense, Heather. It might take some time. I know when I was a student at this level of class, this kind of stuff would have scared the you-know-what out of me, and I would have been lost. But it is something that we should know how to do, even if it frightens us. Any other questions? All right, well, we're officially out of the allotted 20 whiteboards that Zoom provides us. And so what I will do is post the next homework. Hopefully you'll work on it. If you have any questions, just email me. I'd be happy to answer them. And if I don't respond in an hour or two, send the email again, and I will get to you as soon as I can. All righty. All right. Well, then I will talk to you guys. What is today? Tuesday. So Thursday, hopefully. All right. Thank you guys very much. Take care, and let me know if you have any issues. I will talk to you Thursday.